So, good afternoon, everyone. I'm Yifeng from INFN LNS in Italy. I'm glad to be given this opportunity to talk about the chirokinetic studies of spin polarization. The work is based on my collaborations with Shuai Liu from Institute of Modern Physics and also Professor Chuoming Ko from Texas A&M University. The talk is based on these three papers. Now let's begin. We know in non-central heavy ion collisions, there is a vorticity field generated along the direction of angular momentum. There are a lot of ways to calculate the vorticity field in heavy ion collisions. For example, based on AMPT model, this paper shows the time evolution of the average omega y. It shows the time evolution, and also it shows that with the increase of the collision energy, the vorticity field becomes smaller. And we know for particles with spin, it should be polarized in a rotating matter. And in fact, the star mirrors the spin and polarization of lambda particles. They found a non-zero spin polarization of lambda, and also they found the spin polarization is smaller for higher energy. And this agree with this picture. In the theoretical studies, usually people use this formula, and the center part is this thermal vorticity. And it is calculated as the phase out of the lambda and assume local equilibrium. And we know for quarks, it also has spin. So in QGP phase, it should be polarized also. And because for UD and S quarks, they have very small mass. So we can adopt the chirokinetic theory developed in the last decade to study the spin polarization also. And in fact, we just adopt the chirokinetic theory and study the lambda spin polarization, the global one. And we also agree well with the experimental data. And now let us discuss the chirokinetic theory and our development of transport model. First, I want to point the connection between spin polarization and the chiromagnetic effect and the chirovertical effect. And first, let's choose only massless right chirality particle, which is right-handed, and the right chirality antiparticle, which is left-handed, to illustrate it. If we have a magnetic field, so for the positive charged particle, the spin is along this direction. Because it's right-handed, so momentum is also along this direction. But for negative charged antiparticle, spin is opposite. And because it's left-handed, so the momentum goes this way. This can give you the current, which is proportional to the magnetic field, and also the coefficient is the Q, mu r over 4 pi square. You see, if mu r is 0, then the G is 0. It's because when mu r is 0, you have the same number of particle and antiparticle of right chirality because they move in the same direction, so there is no net current. And also, if you study the left chirality antiparticle and particle, you will have a negative sign here. And of course, if you add them together, you will get this chiromagnetic effect. If you subtract them, you will get this chiral separation effect. This GA is called a chiral axial charge density current, and also it is just a spin polarization density. And for the vorticity, you see if there is an omega in this direction, then spin of a particle, antiparticle all polarized in along the omega. But for this right-handed particle, momentum goes this way. But for this left-handed antiparticle, momentum goes this way. So you can find a GR, which is proportional to the vorticity, and also this is the coefficient. For the left-handed particle, antiparticle, you will have this formula. Then if you subtract them together, you will get this axial current, and In fact, this is the chiral vertical effect. You see it's non-zero when temperature and chemical potential is zero. Usually when you derive the above equations, there are a lot of methods, and in the last decade, a lot of them focus on the derivation of equation motion for massless fermions. And here I showed several papers, but there are more, and I don't include all of them. And a formal way to derive the equation motions is based on this Wigner equation. And in this paper, if you assume the system is closer to the equilibrium condition like this, then you obtain the covariant form for the equation motion of the position and the momentum. Then they found that if you integrate over the D4P, you will get this covariant form for the chiral magnetic effect and the chiral vertical effect. And usually in transport model, we need the 3D form. So they integrate the energy part, and then you can get this 3D form. In 3D form, if you want to evaluate the current, you need not only include, you should include the addition term, the square root G. This is called the phase space mirror, and it is just equal to dt over d tau shown here. But the above equations have some problems in transport model. This is like a typical transport model. In the right hand in the left hand is the equation motion. In the right hand is scattering. Like here we show a typical 2-2 scattering. If you only modify this side for the equation motion, but not this side, you will immediately find it doesn't conserve charge. You can see it by integrate this D3P and times the square root G. You will see on the right hand, there is this term up here. If in the normal collision and the normal equation motion, there is now this term. So this is a total anti-symmetric if you swap AB to CD. So this means that this term is always there, no matter what collision, no matter what kind of distribution function you have. However, if you modify, you include this term, this is not a total antisymmetric. So if you so this means if it's not in equilibrium, this term is non-zero. So you have a charge non-conservation. This bothers us, and however, usually people don't discuss the collision term in the chiral kinetic theory. So in these two papers, we just overcome it by multiply by these three more terms here, so that we make sure it's a total symmetric, and then you can always conserve the charge. Then further, we redefine the distribution function. So the equation motion will look like this. And then we just solve the equation motion for this capital F. When you evaluate current, then you don't need to include this square root G. It automatically includes in the scattering. So if there is no collision, then the particle's momentum will be like the same before. So it will include some non-equilibrium effect. And this strategy is adopted in the first two papers, in our first two papers. And we found there are good agreement with the experimental data. However, though it can reproduce experiments, a lot of experimental data, there are still some theoretical problems. Like here, first is the connection to the thermal vorticity. This is what is for the axial current. You see, this is the coefficient and this is the omega. The omega is here is thermal vorticity. And then we want to find what it is for the from the thermal vorticity. And this is the formula for the thermal vorticity from this famous paper. And we know here, this is thermal vorticity. Here there is a mass term. Because there is mass, so you cannot apply to massless particle. So then however, if you look at the Pauli-Luberansky vector, you will see that it's a total, then you will see it's just like this. So there is no mass here. So you can apply this Pauli-Luberansky vector for both massless particle and massive particle. Then for massless particle, you integrate over this D4P, you get the same same formula. However, this omega is not the kinetic vorticity. It's a thermal vorticity times temperature. So we know only one has to be true. You cannot have both of them correct. And of course, when they derive this formula from the equation motions, this is the constraint for the equilibrium conditions. And if you remove this constraint and change this constraint from the flow to the flow over temperature, then you should, these two should be the same. Then this means you can replace this kinetic vorticity with the thermal vorticity times temperature. However, if you look at the polarization before the integration of over D3P, you see they are still not same because like here, you see there is a 1 minus F like here for the Fermi-Dirac equation. However, if you look at this side, there is now this term. So in momentum space, they are not same. And also for free particles that do not interact with other particles, they do not feel the vorticity. So there is some discontinuity from the equilibrium to non-equilibrium conditions. This persuades us to find a more natural way to generate a spin polarization. And if you know the transport model, if you force the energy and the momentum conservation like here, then in the thermal equilibrium, you will find the distribution looks have this form. And also, if in the collision kernel you have this kind of symmetry, then the distribution is just a Boltzmann distribution. And if you include the Pauli blocking term, then you will have this Fermi-Dirac distribution. And so if you include, if you force the total angular momentum conservation, then naturally you will generate this spin polarization. This is a spin tensor, and omega is just, you can call it a spin chemical potential right now. And later we'll show what it is. For massless particle, the spin is slaves to the momentum. So this N is always like this in all frame. And then we can immediately find that in collision, in scattering, the orbital angular momentum and the spin angular momentum have to mix with each other. You can see it here. We prepare two particles head-to-head collision, and they have both have a positive helicity. So the initial spin is 0. If you assume they collide at the same point and outgoing at the same point, then afterwards the spin, one goes this way, one goes this way. So the total spin goes this way. So you do not conserve only the spin angular momentum. So you can only conserve the total angular momentum, and you have to borrow some orbital angular momentum into the spin. And in fact, so if you have a rotating matter with only orbital momentum initial, then from the scattering, it can lead to global spin polarization in the scattering by converting orbital to the spin. And usually when we deal with scattering in the deal with scattering in transport model, we deal it in the center of mass frame because it will be simple. And if you want to conserve the total angular momentum, you can also do it in the center mass frame because it is simple and it guarantees the covariance. However, when you boost a particle from the level frame to center mass frame, the Lorentz boost can induce an anomalous set jump effect for massless particles. You can see it here. This is like the spin. If you force this spin is like a tensor, then you see if you boost it in a different frame, the spin is not a slave to the momentum. However, we know for massless particles, spin is always either along or opposite to the direction of momentum. So this means you cannot, this is not a tensor. You have to borrow some orbital angular momentum to the spin so that though it is not a vector, it's not a tensor, the spin is still slave to momentum in a different frame. This is what it's like for the set jump. This is the additional one. It has this form, and you will find that it's just proportional to, it's particular to the momentum. And we know, however, the total angular momentum is a tensor. And it may seem strange that there is a set jump when we boost. The problem is that when we do not usually clarify the meaning of position in transport model. We should know the position should be defined clearly, like as the average position of some quantity, like charge density or energy density, and so on, especially for a particle with spin. For example, like in this paper, they choose the Dirac particle, which is a wave package. Initially, they have a spin in the direction, and the center is just in the center. So the average position is 0. Then they boost along the positive X direction. Then they look at the probability density. They found the center moves to the positive Y direction. So this is just the set jump. Like if you define it as the average position of charge density, then it is how it boosts. And let's see what is the equilibrium conditions. In thermal equilibrium, the distribution function should be looks like this if you conserve energy momentum and also the total angular momentum. And if you do it in another frame, you should know in equilibrium it should be always like this formula. And from the set jump, you know this is how distribution boost. It's not a Lorentz. It's not a Lorentz invariant. So you relate this G prime to the original G. There is a Lorentz. There is a set jump here. Then you rewrite it, and you will see there is an additional term here. So if in equilibrium, this term should be like exactly 0. This means this omega mu nu is the spin chemical potential. It should be just the thermal vorticity. And also it constrains the flow as this one. So right now we see in this method, the correct one is thermal vorticity. And also it constrains the flow. However, this constraint is very strong. For example, in MPT model, it doesn't satisfy this constraint. So this means the non-equilibrium effect should be important in heavy oscillations. And then you need to find the axial current or the spin polarization density. Normally we can just use this P mu and times lambda to get the axial current. However, you will see if you only use this and you assume the distribution function have this kind of distribution function. Then you will see the total spin is just one third of the total spin that you can find from the thermal vorticity. And in fact, in this paper, they showed that there is an additional term, like the set jump term, you should include. It's because if you only have this term, it's not a Lorentz vector. This one is vector, however, F is not. Only if you add them together, you will have a Lorentz vector for this G mu. And of course, you can understand this just from mathematically, like this is a current operator. Then if you use the Gordon identity, you will rewrite it in this form. So this form is just the P mu term, and this term is just the spin term, or the magnetization current. And because there is a mass here, so this is a massive case. For massless case, you should rewrite this mass to the energy, and this phi bar to the phi dagger. Then this one is just the same as this one. And also, you know, for massive particle, the current and axial current has no relation. However, for massless particle, they are just differed by this helicity. So the axial charge current you can calculate from this formula only for massless particles. And then we have this distribution function, and we include it. You will see we can then find this spin polarization. This is exactly the one from the thermal vorticity. Here we discuss some details of how we conserve total angular momentum in a scattering in our transport model. We conserve, like here is a spatial component. Then it should be conserved before and after scattering. And because of this constraint, you will see the momentum is just a rotation around this total angular momentum. And also the delta prime is also just a rotation around the total angular momentum. The delta is just the difference between the position of a colliding particle before and after scattering. And also for the time component of the total angular momentum, you can have this formula. Then after this, you can conserve the total angular momentum tensor. And then you need to boost everything from center mass frame to the lab frame. And then you will see that the time is not like the same before and after the scattering because this the position and the momentum change. So you need to propagate the particles back to their collision time along their world line, so they scatter at the same time and conserve total angular momentum. Now we apply the transport model to heavy ion collisions. And in this paper, we do not include the total angular momentum conservations. And this means the vorticity is treated as an external field, like EM field. The vorticity is given by this formula. The U we find like locally, we calculate locally from our transport code. And so this means that the relevant in this paper is the kinetic vorticity. However, you see they can also reproduce data quite well. Now, if because we study the average spin polarization, so we do not include the EM field. This is the equation motion. And also we include this modified scattering. This can make sure the charge conservation. And also it tells us if there is no collision, then this momentum doesn't change, so spin there is no spin polarization. You can only generate the spin polarization through the scattering. This can kind of include some non-equilibrium effect. And here we show like the normal collision plus this chiral equation motion. So you can generate some spin polarization from the chiral vortical effect. However, you should include the collision term, then you can quickly approach generate spin polarization. And you see these two, we generate at this 7.7 GeV the spin polarization around the experiment data for like UD and S quarks. We also see S quarks is smaller than UD quarks. It's because in MPT model, S quark have a different coordinate distribution as the UD quarks. And also we include some math correction to this equation motion. And then we need to calculate the lambda polarization from the quarks. And this we use a Coalescence model. Usually Coalescence model only deals with the position and the momentum. There is no spin. So here we just adopt the non-relativistic spin addition. This means we first for quarks spin, it's along its momentum. So you can use this wave function to represent it. The theta phi is like the azimuthal angle for the quark spins. And then you have this wave function for all quarks, and then you find the projection to the hadrons. For lambda, because its spin is totally determined by S quarks from the constituted quark model. So UD quarks forms a spin singulator. Then we first find how UD quarks for the probability for UD quarks to form the spin singulator. Then this is the wave function after the spin singulator wave function. This is like a quark. So you will see it's like this. If they have the same direction for the spin of U and D quarks, then this is 0. If they have the opposite direction, this one is maximum. So we find the probability for UD quarks, UD and S quarks to form lambda. And then the spin is just determined by S quarks. And here we show the total spin polarization, like of lambda. There is no feed down effect in this figure. The feed down should bring it down by 20%. And we see our results kind of agree with the experiment data. And we also studied the spin polarization as a function of PT, the global one. Then we see that it's almost flat with PT. And here we saw the spin polarization at 7.7 GeV. And we found the polarization at mid rapidity is maximum. However, it's smaller at larger rapidity. At higher energy, the spin polarization looks like this. It's more flat and smaller. Recently, people always talk about the local spin polarization because it has rich structures. And for example, in this paper, use the freeze-out profile in Hydra. They predict the longitudinal spin polarization in the first and third quadrant is negative, and it's positive in these quadrants. This is a star measurement, and they found, however, this is positive in these two quadrants. This is opposite to the prediction. You may wonder what happens for other freeze-out profile. In fact, in this paper, they use MPT model to generate it. They also found it's negative. It's opposite to the experiment data. Also, they predict the px and the py like as a function of an azimuthal angle, which is it's odd in rapidity function. So we also study this problems using the chiral kinetic equation. This is still using omega as external field. So we first look at the PZ, we find our results are just agree with experimental data in trend and also magnitude. Also for S-quark, it's like this. It's a little smaller. We know we also use the MPT model to generate we use the MPT model as the initial conditions. So we should know why we have a different results. Then we first look at the time evolution of PZ at like px and py larger than 0. This is these quadrants. So we see initially it's negative. However, it becomes positive later, and because omega is external field, so we can the U is like we can study omega x, y, z separately. Here, first we show omega y, omega z effect, the green line. It is a small negative. And if you look at the omega z at this x, at x times y larger than 0 quadrants, then you will see it's negative. However, you see it's very small because of this omega z. If you look at the effect of omega x, it's like give a positive PZ, and omega y is negative. Then you see why this omega x and omega y have a larger effect. It's because omega x and omega y is like approach maximum at the beginning, but omega z is only at a later time. So because we include some non-equilibrium effects, so these two terms dominate. And also you see at a later time, omega x dominate over omega y and omega z. So that's why we have finally the dominated by omega x, and initially this is omega y is the maximum. So we have a negative there. We can also, in this picture, because in this picture, we can like make a prediction at a smaller absolute value of rapidity. The PZ is smaller. However, the star also mirrors the Py as a function of azimuthal angle. They found the Py is maximum here. And from the chiral-kinetic equation motions, we find this is our result. It's just opposite, so we cannot reproduce the experimental data. The reason is very simple, because we in spin is always along momentum. So when phi is 0, there is only px and no py, so the spin is 0. And of course, you can redefine the spin, but the most correct one is the covariant angular-momentum-conserved transport model, like we studied from in this paper, and we discussed that before. Here we first check in our numeric code. So we see that we prepare a box with some vorticity. So we have initially only orbital angular momentum, but the spin is 0. Then turn on the scattering, you will see the spin is increased faster and then approach some limit. And orbital angular momentum decrease and then approach some like limit. However, if you look at the total spin, is total angular momentum is always the same. This make sure our code is valid. And also here we check our spin polarization. This red line is just the normal spin, and this one is from this one. And you see this one doesn't change too much because the fireball doesn't change too much, but the spin it changes, it increases because of this. And if you add them together, you will get the total spin. You will see this green line is what it is from numerical study, and this line, black line, is from the thermal model. You see these two agree with each other very good. Then we applied it to heavy ion collisions. We first at 200 GeV, we first check it can how it can it like mimic the effect of a chiral vertical effect. First, we know in non-central heavy ion collisions, the vorticity is along negative y direction. So this means through the chiral effect, there will be more right-handed particle in the negative y direction. In fact, if you look at our from simulation at t equal to 3 Fermi over C and 8 Fermi over C, you will see like it's just like this. Also, you have this local structure for the vorticity, for the transversal vorticity. When in non-central collisions, these omega x, omega y does not cancel exactly. So you also expect some quadrants for the axial charge density. And in fact, we found there is no quadrant like at initial time, like t equal to 3 Fermi over C. But at a later time, you will see the quadrants, it happens. And finally, we study the local spin polarization of Py and Pz. This is for the quarks in the rest frame, because in the particle, in the medium rest frame, the spin polarization of quarks should be similar to the polarization of lambda in the rest frame, in particle rest frame. And here, the red line is the normal spin, and this one is the the orbital part. And if you add them together, you will see this total spin. You see there is a negative of global spin polar. There is global spin polarization in negative y direction at t equal to 3. However, the trend is different from the experimental. And for Pz, is also different from experimental initially. However, at later time, you will see the global polarization is like similar. However, the trend is changed, and it's agree with the experimental data. And also for the Pz, the trend changed and also agree with the experimental data. And I want to make a comment. We know we also have the thermal vorticity. However, it has to assume the equilibrium conditions. And the equilibrium means this is like how the flow. Because we know this may not be correct in heavy ion collision. So this means we may not be in equilibrium. So this is maybe one of the reasons why we are different from other calculations using MPT model and directly use thermal vorticity. And also this model can modify the equation motion of fireball because it can also modify the energy momentum tensor of the, it can also modify the energy momentum tensor. So it can change the evolution of fireball. It is not like the normal one. And maybe there are other reasons, and we should discuss, we should study further. And here is a summary. And of course, there are more things to do. Thank you.
Okay. All right, thank you very much for a very nice talk. I already saw a few hands. Enrico, you want to start with your questions?
Hi, yeah, thanks. Could you please go to slide 13?
13?
13, yes. Yes, so here my question is a bit naive, but so you with the coalescent model, you say that you basically need to assume that the quarks are not relativistic.
Yeah.
But how is this not a contradiction with the fact that the quarks in all your evolution are ultra relativistic? So,
yes, in fact, this is a good question, and in fact, we should modify this from the relativistic to the non-relativistic. But however, if you study the spin polarization, like the global one, usually this is you can it's not make a big problem.
Okay, so you see that since you can somehow have the right pattern with the global polarization, then why not using also for the local polarization and so on?
Yeah.
May I comment on that?
Yeah. Yes.
The reason is in the chiral kinetic property assume quarks are massless. Of course, he did not include in the pion condensate those things. It's non-perturbative. We must have a pion condensate there. That's not included in the present study. But the current quark mass is always small, and that affects the what's the helicity, right? If you take the current quark mass 0, then of course the spins always along the momentum directions. Yeah. But still there are condensates. What happens when you include condensates, then at TC, at the hadronization, then that gives the constitution quark mass, right? Yeah. And that you use for the coalescent. The coalescent model is based on constituent quark masses. And of course, as Yifeng said, it's still a lot to do. But okay. The idea is the following: the LTC somehow would just put back the condensates associated with the quark, give it the constituent quark mass, then do the coalescence.
Okay. May I also ask another question? Another quick question?
Yeah.
Can you go to slide 8? So here you were mentioning the side jumps for massless and massive particles, right?
Massive, yeah.
But so I'm a bit skeptical about this side jump of the massive particles, because so this S mu nu, this tensor S mu nu, in principle for massless particles, it must be a non-covariant object for massless. But for massive, you can actually find an S mu nu which is covariant. So
yeah.
Then why would you use the non-covariant one for massive particles? So you, with the proper pseudo-gauge transformation, if you change the orbital and the spin angular momentum, you reshuffle them, you can actually define an S mu nu which is covariant for massive particles.
For massive, I think if this your comment is only for massive particle. For
yeah, for massless, absolutely agree that there is no way. Yeah, but the one on the right is massive, right? So what is actually depicted on the right hand side? On the right panel, sorry, on the right figure.
Oh, on the right hand, it's massive, but you can also apply for massless, because I mean, if for S mu nu let, if you want it's covariant, you have then the position you defined, in fact, it's not like the canonical energy density, like average position. So then it's a covariant. However, if you use the like axial current, axial energy, the canonical energy density, it's not a covariant.
But for massive particle, I mean, one can find
you can find
it's covariant, so you actually wouldn't see any side jump. So I'm not sure what is on the right panel is. For massless, I totally agree. Yes. For massive, I'm not sure.
I mean, for massive, this is because this is like canonical, like energy density.
I think what Enrico is basically saying is that for massive fermion, there is no need of side jump.
Exactly.
Whether you agree or not.
But you know, they are like same in equilibrium, so you don't need to worry. Like
no, just because, okay. Maybe we can discuss later.
Yeah. Okay.
Yeah. Thanks.
Maybe I'll move to the next question.
Yeah. Thank you.
Masood, yeah, you want to ask your question?
Hi.
Hi.
I want to ask two naive questions, one about page 5 and one about page 10. Yes.
Yeah.
Here is page, yes. Here, actually. The equilibrium constraint. You said that here that d sigma t is equal to 0, but actually I think that this is in general, this is d sigma t plus t a sigma, yeah? Because there is no, apparently there is no reason that we believe that in equilibrium the spatial gradients are zero.
I'm sorry, what's your question?
My question is why you think that the sigma, I mean the,
this one?
yeah, this guy is going to be zero, because what you find in equilibrium is the sigma t plus ta sigma equal to zero.
Yeah. I can answer this question because this is our paper. Yeah, in this paper, Yifeng. So this is our paper.
Yeah, this
should not the in PRD paper in 2017 we use the thermal vorticity. Actually, partial rho beta sigma, partial sigma beta rho, and this is the condition is what we used in our PRL paper in 2012.
Yeah.
At that time, we didn't realize that the thermal vorticity will, it is the correct thermal quantity. Therefore, we just assume that the partial sigma partial t is zero. This is the aim of that paper is to derive the CME and CVE. So we get using this condition, we can simplify our Wiener function solution. Therefore, we find the correct CME coefficient and CVE coefficient. But this is actually has a flaw, which we made up in this PRD paper in 2017. Actually, in that paper we remove this condition partial sigma partial t is equal to zero. Remove this condition and replace u to beta.
Yeah.
Actually, it's the thermal is a killing condition. Yeah, this is the history. I mean.
Okay. But can I ask my next question?
Yeah.
On page 10.
Yeah, go ahead.
10.
As I understand, this is on page 10. You're essentially defining a covariant derivative, yeah?
This one, yeah.
Yeah, because it's a covariant derivative, and it's coming from where?
It's because this f is not a Lorentz invariant. Like it's supposed like this.
So I was thinking that is that related this covariant disconnection? I mean, as mu nu is working like a connection here, yeah.
Right. So basically, GMO5. That's because if people want to formulate this chirokinetic theory in more like a 3D kind of formulation, the F itself is no longer Lorentz invariant. It's not a Lorentz scalar, but GMO5, the physical current has been Lorentz covariant. So that's why you need this extra term here. Anyway, I think that's a general issue with this kind of 3D formulation of the chirokinetic theory. If you use the Wigner function formalism like totally covariant, you don't need this.
Thank you.
Yeah, maybe we move on to the next question, and for the rest of the questions, try to be quick because we have a discussion session later. So Dylan, go ahead.
Yeah.
Can you hear me?
Yeah.
Yes, thanks for the interesting talk. So I also, just maybe at this page. So for this actual charge current density in the phase space is by Chen, and also from the Wigner function approach. If maybe this is more like a common. If this F now is out of equilibrium, then this spin tensor does not only couples to just this gradient, and it also has the collisions on top of that. So it will couples to also collisional kernel. Perhaps you can drop it based on the weakly couples argument. I don't know, but in principle, this spin tensor should also couples to the collisional corrections in these equations.
Yeah. In this paper, there are also the collision term. However, here we just like.
Okay. Okay. Yeah. Just a comment. Okay. Thank you.
Because when you include the collision in the charge conservation, should be carefully studied.
Okay. So next question, Trin, you still have a question?
Yes, I have a question. So in your calculation in your calculation of the collision terms, how do you deal with the at the 200 GeV, for example, you should have quark almost equal number of quarks and equal number of anti-quarks. So how do you did you include the annihilation and the creation processes?
No, we only include the 2-to-2 scattering.
But this is also they can undergo the 2-2. So for example, one quark and one anti-quark through it and becomes another quark and anti-quark.
Oh yeah.
This is called annihilation process.
Yes.
You include all the 2-2 processes, right?
No. In fact, this is like just the elastic collision.
Yeah. This is for example, U and U bar.
Yeah.
Collide, annihilates to a gluon or a photon, then comes U and U bar. This is a annihilation.
Yeah. But I mean, because we don't deal with the intra process. We only deal with the final and the initial state.
I see, but you have a quark and anti-quark, right?
Yeah.
So how do you treat the quark, the interaction of the quark and anti-quark?
In fact,
it's the same as you deal with quark scattering.
Yeah, we use the same thing. It's like only here. We just need to conserve the total angular momentum.
No, this is not my question.
Yeah, can I answer for him?
Yeah,
I think he doesn't have first UU bar because in the model he has no gluons, only have quarks, anti-quarks, but he also ignored the flavor exchange. The QQ bar, UU bar can go to SS bar, SS bar can go to DD bar. That he neglects. All right.
Okay.
No gluons.
So only. But what's the medium? I mean, what's do you have a? Yeah. This is all the quark scattering through gluon or through photon.
No, he just parameter cross-section by some numbers, 10 millibar. There's no explicit calculations.
There's no.
Yeah, eventually one need a model to calculate median cross-sections. Nobody. I mean, we have to be very careful because they're still maybe strongly interacting. So use a particular cross-section may not be valid. Right? So it's a parameter. He fitted the V2 he fitted the quark V2 to the pion V2 in some sense.
So it's not QCD scattering, right?
No.
It's just okay.
Yeah.
Yeah, they just have an elastic scattering with some given cross section. That's my
Yeah.
I see.
It's kinetic scattering. Let's say, yeah.
Okay, so that's it. Thank you.
Okay, so I think so. Two really quick questions. So Francisco.
Yeah, can you hear me?
Yeah.
Yes.
Okay. So can you go to slide number 16? Oh, maybe I made a mistake. So can you go ahead?
Go ahead.
Ahead. The formula. This is the formula where you show. Oh, maybe 21. Sorry, 21.
21.
Yeah, this one. Yeah. So So there's something I want to ask you about this vector p mu. I mean, this is not p mu, but I mean, it's a vector, right? Because that you have J5.
You mean this p mu, yeah?
No. Yeah, I mean, the formula, you wrote P equal D3X J5. In the row below. Yeah, this one, yeah. So I guess this is the polarization vector, isn't it?
Yeah.
Okay, so then the momentum dependence, since you are showing the plots with the polarization as a function of momentum, the momentum dependence is encoded in this function J mu X and P. So I guess that J5 is a function of X and P in your formula, right?
Yes. Yeah.
Okay, so the question is, if this is so, so I have the impression here that this vector is not orthogonal to P mu, as it should be.
Oh, what?
Because if you multiply...
That's a typo. That's a J50. That's a typo. The polarization, the spatial integral J50, not the J5 vector.
This is
that's a J5 vector. That's correct. Yeah. All right.
No, I mean, I have so the question is the following: is that if this is the case, so if P mu is equal to D3X J5 mu, and if J5 mu is proportional to P mu, I mean, as a term proportional to P mu, like that, and S mu nu, it cannot be. It cannot. So it looks like it's not orthogonal to P mu.
Orthogonal to P mu.
I mean, it should be orthogonal to P mu for a massive particle.
Oh, let me see.
You know, what I mean is the following. If, for instance, if you look at the formula that you wrote in the middle of the page, J mu 5 equal lambda P mu F naught plus 1/4. Can you see it? That it is in the middle of the page.
Where?
On your right column, middle of the page. J mu 5 equal lambda P mu F naught.
Yeah.
Okay, yeah. So the second term is orthogonal to P mu.
Oh.
The second term, because of the Levi-Civita tensor. Then it becomes orthogonal to P mu. Right?
Yeah.
Because if you multiply by P mu, then you get 0.
Yeah.
Okay. Which is fine. Which is fine for a massive particle. This is what you expect. But the first term is not 0 unless it is a massless particle.
This term is not 0.
Yeah, because if you saturate with P mu, then you get lambda m squared F naught.
Okay.
And so I was wondering whether this term plays a role in this formula, because this would be somewhat sort of say clash between the definition of the polarization vector for a massive particle and its properties.
But this term should be 0 because this you have positive helicity and negative helicity.
So I don't know. This is what I'm asking, maybe.
This is 0. Only this term is non-zero for both mass, for right and left helicity particle.
So do you mean that? See, this is what I don't understand. Maybe.
So you're saying you have an equal number of lambda equal to plus and lambda equal to minus, and you add them together. You're claiming that they're 0.
Ah, so he sums over lambda.
Yeah.
Lambda is like chirality, or let's say plus and minus 1.
Ah, okay. I see. Okay, that's okay. Thank you.
Okay, maybe last question, quick question. Oleg, you want to ask your question?
Thanks. Actually, I think I have a similar question. Maybe two related questions to the same slide. And indeed, if you calculate the axial charge, it is 0 component of axial current. But 0 component of polarization vector appears only if particle is moving. If particle is at rest, the 0 component of polarization is of course 0 because vectors are orthogonal. And then we actually used the similar formula, similar equation for axial charge for our calculation with chiral vertical effects. But to take this into account that particles have to move, we somehow just make a kinematical boost. And in the talk of Yuri yesterday, he just accounted this by moving to the rest frame of the medium. And related questions, in the denominators, which particles do you take into account? And I am asking because in order to accommodate, to describe the enhancement of lambda bar by this formula, it's necessary to take into account also vector mesons, K-star mesons. Because otherwise, if you calculate this for anti-lambda, the polarization is enhanced, I don't know, 10 or 100 times. So these are two related questions. They're taking into account the boost in order to accommodate for axial charge, and which particles are taken into account in the denominator.
In fact, here we only discuss the quarks polarization in the.
This is only quarks, because we use it also to calculate the hadronic polarization finally. Yes.
Yeah, we should develop the relativistic coalescence like to.
I see, but so instead of this, we used a sort of duality for axial charge, a sort of 't Hooft principle, and so we used it also for hadrons. This is the answer for the questions. But maybe because quarks are massless, maybe this is also answer to question of Francesco, because really it's massless particles, so it's orthogonal in this sense, I would say. So you use this for quarks, right?
Yeah, this is the quarks.
I see. But so we used it for hadrons, and it's also more or less works as Yuri showed yesterday. Okay, thank you.
Okay, so let's call it the end of the talk. So let's thank Yifeng again.